All right. Hi, I'm Chris Brown, and this is lecture 2.16a on machine surfaces in axiomatic design of manufacturing processes, a grad course here at WPI. So we're looking at the surface that forms when we run a tool across a workpiece and create a chip. Here's the tool. And this funny yellow dippy thing is meant to represent the kind of surface that is caused by the tool nose here. So here's where the tool is forming the chips and they're falling down. And then it puts a series of cusps into the surface. And as it's feeding this way, it leaves those cusps behind. So flipping this over and going the other way now, it's feeding in this direction. And here's the tool. Here is the old surface of the workpiece, and here's the new surface. And so this is the chip that is forming, and these are the cusps that are left behind. Now, in the classic definition of machine surface roughness, we look at RZ, which you will recall is the peak to valley roughness. And so here's the peak, there's the valley, there's the RZ. And this can be related to the tool nose radius and the feed per revolution. And this is done, and we'll show you in a moment how that is done. Now this takes no account of the built-up edge, tool nicks, which would be imparted here on this surface, or interactions with the microconstituents in the workpiece, which can also show up here, or any kind of chatter, vibrations, and so. The other point to note, when we studied the chip formation, we're studying this region in here, the bulk of the chip, where the bulk of the force is being generated. But right here this is where the surface is being generated that we're leaving behind. This is the surface we're going to use, right here at the tool nose. And this is a much more complicated deformation zone than this one up here, because it's trying to shear that way and shear that way. And so, okay, and there's the feed. So, so this is what I'm going to call the primary roughness and turning. And again, we work this out from using triangles, as we saw before, the geometric kinds of relationships that triangle things are helpful. So we're using the Pythagorean theorem, and we're saying that this R here is equal to this leg squared plus that leg squared, the Pythagorean theorem. Then when we expand these terms, drop the higher order terms, we end up with the peak to valley roughness is equal to the square of the feed divided by 8 times the tool nose radius, which is here. All right. So here is a measurement of an actual machine surface made with a scanning laser confocal measuring microscope. And so we can see here the ridges between the feed marks. Here's where the tool went. And we see there's a lot more going on. We're not seeing something that's perfectly smooth. The material is 6061 T6 aluminum. This is a common kind of aluminum that's used in some sports equipment and used in our machining lab for students' project work. So this is the scale at which the regular geometry dominates as we go on the scale of the feed. So this is a regular geometry caused by the tool nose, although nonetheless it is called in all of the textbooks machining roughness. And it ignores the chaotic processes. Now remember, some people think that a rough surface must be chaotic, and that however, engineers often say, well, just as long as it's fine scale, we'll call it roughness. And so this is, in this case, this is being called roughness, even though the chaos comes in at a much finer scale. We're going to see how this limits the finish. And I think I mentioned most of these things previously. Here's another depiction of a turned surface. And so we're looking at this at an angle. One of the nice things about a confocal microscope measurement, or any kind of 3D measuring microscope, is that after you've made the measurement, you have the 3D coordinates of the measured surface. And so this you can twist around and look at different angles and fly through and whatever you want to do. So here we can see, here is the tool nose radius there. And this is slightly distorted in the vertical direction, more than slightly, because there's the vertical axis, there's the horizontal. So that these are highly exaggerated. Excuse me. So here's something we'll have a look at in more detail in the next lecture. This is a new way that we've developed here at WPI to represent curvature on the surface. We're taking a profile across here, and this is the curvature, which is 1 over length units, and this is the scale. So if we look at this at a large scale, it looks flat, basically, and that's what we're seeing out here. And as we go to finer scales, these are negative curvatures, these ridges, and we can see those persist to the finest scales. These are positive curvatures, and we've got sort of little curvatures on big curvatures, as you can see as we go from the coarser scales to the finer scales. And these little curvatures on big curvatures develop naturally as we go towards the finer scales, which is what we'd expect. So this is an interesting representation of the machine's surface using curvature as a function of scale and position across this way. Here's some macrographs with scale showing the difference between a feed of 10 micrometers per revolution and a feed of 250 micrometers per revolution made with the same tool. So here it's almost too small to make out the grooves, and here we can see the grooves quite plainly. Here is a tool. I think it's similar to the one that was used, or it's used anyways before it got used perhaps. So it's Kennametal with this designation, and the tool nose radius is about 400 micrometers. So that's this radius here. This is the tool edge radius here, and then here's a chip breaker further back. And it was turned on a Haas SL10 CNC lathe. Now here is the tip of the tool measured with a microscope. So the tool radius is in this direction, and the nose radius, the edge radius is around this way. So it looks actually quite coarse in this representation. So there's the edge radius. Here's the rake face of the tool. There's the flank face. And here's a representation of the tool as curvature along a line like that. So we can see that this curvature of the edge persists to quite fine scales, as we would expect, because it's a major curve there. As we get out on the rake face and the flank face, we're seeing this little features on big features kind of representation that we also saw on the machine surface. So if we go and try to reduce the feed and see what happens to the roughness, here's the theoretical line, and so it goes to 0. Now, just as the forces don't go to 0 as we take the feed to 0, neither does the roughness. And a better representation of the actual machine surface would be this additive constant, which describes the displacement between the theoretical curve and the curve of pieces that have been actually measured using different feeds, always the same tool nose radius. So we can kind of represent this like this, and this is true for a number of manufacturing processes, and it's been seen in abrasive processes, for example. If we keep reducing whatever process parameter it is that's going to reduce the roughness, there's usually a limit to how far we can go, and some other mechanism is taking over, and it's difficult to get the piece really smooth. And so this line might just have a single slope, and it might be headed towards 0. But something tends to happen as we get to the finer scales, and the mechanism changes. And as long as our tolerance isn't in that region, then we're all set. But lots of times we're trying to get something as smooth as we can. Well, just how smooth can we get something in manufacturing? So here are some pieces made by diamond turning. And this was done at Nanotech near Keene, New Hampshire, by a subsidiary of Moore Tools. Now, one of the interesting things here is we can see some colors. These colors are not due to pigments. These colors are due to very fine scale regularity on the workpiece that is as a result of the machining operation and diffracting the light and reinforcing certain colors. Now, if we take a closer look at this, we can see there seems to be a cross on here, which is blue. And that's because we're looking at 500 nanometer grooves on here, and that's reflecting as blue. This has been faced with the machining operation. So first they went round and round to face this so that it's smooth. Now the material here is electroless nickel, which doesn't have any grains and is single phase. So it can come out as being quite smooth. Now perhaps on your monitor you can't see this, but we can see the rings from the facing operation, just barely out in these quadrants here. And this thing that was giving us the blue light is this series of 500 nanometer grooves, and we've got two series of them going across this face. Now this part is essentially a show-off part to show that you can go across this entire thing, and I forget what the dimensions of this are, but which is actually quite large, and you can do these grooves all the way across, and the tolerances are held so well that they cross in the middle and they hit each other with this 500 nanometers. Now, this was made with a 100x lens and a 2x zoom. So let's go to the limit of what this thing can do. The microscope for measurement. And this is a remarkable measurement with light because this is a 405 nanometer laser. So the spacing is only is less than 100 nanometers larger than the laser light we're using. We can easily see in this how these things have crossed up in the middle, and that this one was done first, this one was done later, I believe, maybe, I don't know. Anyway, you can work it out. So anyway, we can see these details. We can see burrs on these 500 nanometer ridges, and we can see some very fine features on this, which I said is remarkable given that the laser is 405 nanometers. Now, if we look at this seems to be turned 90 degrees from the one we just saw, because we can see these larger burrs here are now occurring up here on this. This is with a scanning electron microscope. Of course, the electrons have got a much smaller wavelength than the light, and therefore we can resolve much finer details, sort of in X and Y. However, there's no direct height information on this, and so I can't take this and twist it around later as I could with the measured surface with the confocal microscope. So here, back to the Lext 4000 confocal, we can see this groove, we can get the depth of the groove, and we can move this around to get different perspectives on it once we've taken the measurement. So here we are zoomed all the way in with a perspective view of the crossed area. All right, so here's the kind of machine that this was made on. These are interesting machines. They're made to be very stable, high precision. Many of the structural components are made with granite rather than steel because it's more stable. So here's a grinding head on this, and here's a ground surface, and you can quite easily see the reflection there. So you can make surfaces that are very smooth and very precise with this. And this is the way this is the kind of machine that is used to make the aspheric lenses that go in, used to make the molds to make the aspheric lenses that go in cell phone cameras, for example. And here is a mold of one of these lenses, a macrograph, and you can see how smooth it is because we're seeing the corner between the wall and the ceiling of the lab that's reflected in this. One of the interesting things about these very fine surfaces, and technically these are very interesting, you can almost see the aspheric wave in this thing, is that these are some of the finest surfaces we ever make, and they're made with abrasives. And here's a different abrasive. This isn't the one that's used to make that, but it's an interesting measurement. The topography is chaotic. It's and basically probably the first material removal operation was an abrasive process, anyway, that man did. Somebody picked up a rock from the ground and started rubbing his stick on it, or vice versa, to sharpen it up, so you had a better chance of getting dinner. All right. So here this is looking straight down. This is a remarkable measurement, actually, with the confocal microscope. It's stitched together, 10 by 10, so there's 100 different images, each one with 1,000,000 elevations, made with a 100x lens. And so this is the actual light, what the actual light looks on this, and you can see the way it's caught some of the abrasive grains. So in manufactured surfaces, there are trends towards better control of surface formation to push smooth and regular form and smooth features to finer scales. Faster, better measuring and analyzing, sometimes done now in the machine tool. And we need a better understanding of the fundamental processes, the tool workpiece interaction, and the surface interactions for performance. Just to acknowledge, Olympus has given the lab a nice confocal measuring microscope to use. Digital Surf provides us with software. Sufina has supported our research in the past. Solarius has given us machines and to use, and Mezzo has also supported our graduate students. And SFRAX is software that we've developed here at WPI and I own. Thank you for your attention.